So the use of molality is especially important as we calculate the collective properties. So here, right, for molarity equals what? Equals the mole of solute divided by volume of solution. So here's the definition, right, for molarity. As you can see, as temperature increase, normally, as temperature increase, the volume will change, and in most cases, the volume will also increase. Why? Why? So, yeah, and then I hope when you learn chemistry, you try to understand the microscopic world. For example, a simple question. Why temperature increase, the volume of a solution increase? Why is that? So, yeah, we need to practice all, along the way. Then you see all these things are not just abstract concept to you, but something understandable and reasonable. Okay, why? One question: why temperature increase, the volume increase? Very simple question. So, as we discussed, either solid, liquid, or gas, right? As the temperature increase, the molecules will move faster, right? And when they move faster, they can what? They can reach a wider range. That's the reason why the volume increase. We need to understand this, not just, temperature increase, volume increase. No, it's not the case. As I use this example in general chemistry 1. So why we put a microwave, when we put a food in our microwave and then we push a button and then the temperature increase. Why is that? Same thing. So microwave is also an energy, kind of energy. When you put your food in the microwave box and you push a button, the molecules in your food gain energy. So when the molecule gain energy, what it will do next? It will move faster, quicker, right? So weight, and then it gains energy, and this energy will eventually be converted to heat. Because the microwave cannot provide energy large enough to initiate a chemical reaction. So it's like we do this, we gain heat, right? The molecule do this, it also gain heat. So that's how it works, you see? It's very reasonable. Okay, so yeah. So yeah, especially if you plan to learn organic chemistry, you need to understand chemistry from the microscope world, not just temperature increase, volume increase. And when we heat with the microwave, then the temperature will increase. But why? So you need to understand the why, the microscopic world. That will help you a lot. That will help you a lot in the long run, especially if you plan to learn organic chemistry or even physical chemistry. Not just memorize. So memorization does not work well in chemistry, I can tell you. It has been proven again and again. Yeah. So you see, as we discussed in this class, excuse me, I need to record. I forgot. Resume recording. Yeah. So as we discussed here, when we put solute in when we dissolve a solute in water or some other solvent, its melting point change, meaning the temperature at which a solid becomes a liquid increase. At the same time, the freezing point decrease. That means the temperature at which solution, melting point, melting point and freezing point are the same thing, sorry. The boiling point increase, the freezing point decrease. You see, all these things, the temperature change, right? The temperature change. Therefore, we cannot use this molarity to quantify. So that's the reason we need to use molality. So molality, we use this lowercase m. Mole of solute divided by mass, kilogram of solvent. As you can see, here molality is independent on what? Temperature, right? Because if you change the temperature, the mass of the solvent does not increase. So then we determine the percent by mass of hydrogen atoms in this solution. So here is mass percentage, right? It's mass. Is mass percentage. Mass percentage, we can do this. Okay. Percentage of hydrogen. Then so mass of hydrogen divided by mass of solution. Then we know the mass of hydrogen is what? 0.94 gram. And the mass of solution, 0.94 gram plus 215 gram, then times 100%. Then we get the percentage, 0.44%. 0.44%. So this, we discussed this in what? General Chemistry 1. The mass percentage, the mass concentration, right? Okay, this is better. This works better. Okay, that's this. Any questions? So, yeah, even if you have no questions, then we'll move forward. The click instead of move on. That's interesting. Okay, here we discuss here the vapor pressure lowering. After we add a solute to a solvent, and after the solute is dissolved, the vapor pressure decreases. Why is that? The reason is very simple. Because the solute molecules or the ions in the solute, you see, block some pathway, right? You see that? It's blocked. Then make it more difficult. And make it more difficult for the what? For the solvent to escape. Very simple. Just block. Okay. Just block. And then here is a quantitative way. Here's Rawls' law. Quantify the pressure change. Okay. Quantify the pressure change. Right? Quantify the pressure change. And you can see, yeah, here we discuss the solute is a non-volatile. Okay, non-volatile. the solute is non-volatile, cannot evaporate. So here, according to the Raoult's law, the partial pressure of a component of an ideal solution equals vapor pressure of the pure component multiplied by its mole fraction. Right? We discussed the mole fraction. So here, here. So the pressure from component A equals the mole fraction of component A times what? Times the pressure of pure A. Pressure of the vapor pressure of pure A. Right? The vapor pressure of pure A is only dependent on what? Temperature and component A structure, nothing else. So, and this means sum. So we have, we have component A, B, C, E to Z, or maybe or even more. Okay. But the thing is that all these solutes are non-volatile. That means they don't generate pressure. For example, sodium chloride, solid, table salt, does not generate any vapor pressure because it is not volatile. It's not volatile. And then eventually, you see, the solution, the pressure of the whole solution equals the mole fraction of the solvent times the vapor pressure of pure solvent. And we can, for sure, this is smaller than 1, right? The mole fraction of solvent is smaller than 1. Because the mole fraction of solvent equals mole of solvent divided by the mole of the whole thing. Solvent and solute 1, solute 2, solute 3, right? So this is smaller than 1. Therefore, the vapor pressure of a solution has a lower pressure than the pressure of a pure solvent. That's called vapor pressure lowering. So here we can, from this scheme, we know what? Qualitatively, that lower pressure lowering occurs in solution. And this Raoult's law can let us quantify. It's lower how much? We can compare. You see, we can calculate, right? So this is a solution. This is pressure of this vapor pressure of the solution equals that much. And then the vapor pressure of pure solvent is P star solvent, because mole fraction of solvent is more than 1. You see, we can calculate. Then, as we discussed, a solute lowers the vapor pressure. As also we discussed before, what's the boiling point? We discussed this, right? The boiling point refers to the temperature when the vapor pressure of a liquid equal the atmospheric pressure. Okay, the atmospheric pressure. So that's called the boiling point. That's called the boiling point. Right? That's called the boiling point. So the boiling point refers to the temperature when the vapor of either the solution, let's put a simple liquid, when the vapor pressure of the liquid equals the atmospheric pressure here, right? And then we can correlate this to what we have discussed, what? Clausius-Clapeyron reaction, right? So for high pressure cooker, the pressure is higher. Therefore, the temperature of water in a high pressure cooker can reach beyond 100 Celsius degree. So at this pressure, the boiling point of water is 100 Celsius degree, right? At this atmospheric pressure, the boiling point of water is 100 Celsius degree. And in a high pressure cooker, the pressure is higher. Therefore, the boiling point of water is higher. Higher than 100 Celsius degree. Why? Because a liquid boils only when the vapor pressure equals the external pressure. Okay, external pressure. Same thing here. We will add a solute. We will add some solute, okay. Then the vapor pressure decrease, right? The vapor pressure decrease compared to pure solvent. And now, if you want to boil this solution, you want the vapor pressure equal, you want the pressure to be equal to the atmospheric pressure. Then you have to increase the temperature, right, to make it happen. Because usually, as you increase the temperature, the pressure increases. You see that? At room temperature, okay, at room temp, not at, let's see, just at regular conditions, okay, at regular conditions. When you add a solute, the vapor pressure decrease. But you still want the vapor pressure to be equivalent to the atmospheric pressure. What you can do? You need to raise the temperature to increase the pressure, to counterbalance the negative contribution to the pressure from the solute, right? As you add a solute, the vapor pressure decreases, but you still want the vapor pressure to be equivalent to the atmospheric pressure, which is constant, does not change. Therefore, you have to increase higher temperature. Or let me jump to this. Here, you can take a look at this energy diagram, phase diagram. Here you see, this is the pure solvent. Let me see. Pure water. Okay, pure water. I mean, here's you see the solid curve representing the phase diagram of what? Pure water. Okay, pure water. And then if you add some non-volatile solute, let's see. Here, the boiling point will reach here. The boiling point will reach here. Why is that? Because when pure water boils, or when the solution boils, the vapor pressure is always here. This is the vapor pressure. Because the pressure, here, is constant. The pressure here, because the pressure here does not change, right? The pressure here does not change. understand. You see, under the same temperature, for example, under the same temperature, here, for pure water, under the same temperature, for example, 100 Celsius degree, it boils, right? 100 Celsius degree, it boils. Oh, sorry. And this is 100 Celsius degree. For liquid water, at this temperature, the vapor pressure is 1 atmospheric pressure. It's equivalent to the external pressure. Then it boils, right? You see that? Here is 100 Celsius degree. This is water, 100 Celsius degree. And then for the pure water, it boils. Why? Because the vapor pressure equals the atmospheric pressure, 1 atm. However, for this solution with sodium chloride or some other non-volatile solute, for the solution at this temperature, the pressure is smaller, right? You see that? It's smaller. It's still smaller than 1 atmospheric pressure. It's here. It's here, right? The pressure is here. At 100 Celsius degree, the pressure of the solution does not reach 1 atm yet. You see that? It's here. It's here. And then if we want to boil, this solution, if we want the pressure of this solution reach 1 atm, we need to what? We need to increase the temperature. If we don't increase temperature at 100 Celsius degree, the solution's vapor pressure is smaller than 1 atm. Why? Because solute lowers down the vapor pressure. That makes sense, right? So you can look at here. 100 Celsius degree, water boils, but solution does not. Why? Because its pressure does not reach 1 atm yet. Because the solute, the non-volatile solute, lowers down the vapor pressure. Okay, lowers down the vapor pressure. So we have to increase the temperature so that the vapor pressure of this solution also 1 atm. Okay, that's one. So the boiling point will increase. And then we use this delta temperature B equals the boiling point of solution minus the boiling point of pure solvent. Okay. So this is the temperature change. Oh, that's the boiling point elevation. Okay, that's the boiling point elevation. It increases. And this delta TB refers to the temperature difference, okay, between the pure solvent and the solution. And then, here how we calculate. This temperature, this boiling point elevation equals the molality of the solute times Kb, constant B. It calls solvent's boiling point elevation constant. So the first lowercase m refers to what? To the molality of the solute. And the Kb refers to the solvent boiling point elevation constant. As you can see from this equation, this temperature change, the boiling point elevation, depends on solute's concentration, not identity. Not identity. And that's the reason we call it what? Colligative properties. Colligative properties only depend on concentration, not the identity of the solute. Then, for this reason, one molality sucrose and 1 molarity ethylene glycol solutions boil at the same temperature. Why? Because they have the same molarity, and they have the same solvent, therefore they have the same solvent boiling point elevation constant. So this kind of property is called colligative property. This property only depends on the concentration of the solute, not the identity of the solute, which is very unique, because usually the identity of a material affect the property, right? HCl, acidic, sodium hydroxide, basic, sodium chloride, neutral, right? This kind of property is not a colligative property, because this property, this acidity, basicity, and all these kind of things depend on what? Depend on their identity. But for colligative properties, they only depend on their concentration, not the identity. Regardless of the, which solutes you use, as long as you have the same molarity, then you have the same boiling point elevation. Okay. So here you can see the boiling point here. The boiling point of solution is higher than the boiling point of solvent, right? Then you can see the former. Can you see from the other one? Okay. So the former is larger than the latter, right? Therefore, this is positive value. So boiling point elevation is a positive value. Yeah. And here, another property is what? Freezing point depression. Freezing point depression. So a solution freezes at a lower temperature than that of the pure solvent for the same reason. And we'll go to discuss the diagram again. So the freezing point depression equals the freezing point of pure solvent minus the freezing point of solution. Again, this is larger. The former is this is larger than that, right? Therefore, this is also a positive value. Also positive value. And we call, again, this property also only depends on what? The concentration. So this freezing point depression equals what? Equals the molarity of the solute times the solvent's freezing point depression constant. Again, this property is also a what? Colligative property. It only depends on the solvent used and the molarity of the solute. And here's the here shows the table. This table lists what? These are the boiling point, the freezing point, and then these solvents, boiling point, elevation, constant, and the solvent's freezing point, depression, constant. Here, we'll use the value here to do the calculation. Okay, to do the calculation here. Any questions? So here's the energy diagram. So here, you see for pure water, at 1 atm, it freezes here, right? It freezes here. So for solution, its vapor pressure is smaller is smaller. Therefore, the freezing point also needs to be lower. To move to this direction, because the level pressure of liquid, of pure water is here. Okay, let me see. Water is here, and 1 atm is here, right? Is here. And then you see this curve can keep going. Let me see. Because at the same temperature, here, if at the same temperature, the pressure here will be lower than that, right? Will be lower than here. The pressure will be lower. Let me see. Should be somewhere here. Okay, the pressure here should be lower. Should be lower than this. Therefore, to reach this pressure, the temperature also needs to be lower. Here, the temperature needs to be increased, and here the temperature needs to go down. Right? So the pressure, if we, let me see, if at the same temperature, the pressure, the level pressure will be lower, will be here. Will be lower. And in order to reach 1 atm, we also need to lower the temperature. It's really different. It's very confusing. I will let you have some time to go through this. Because here we discuss this melting point, the boiling point, all refers to what? Refers to 1 atm condition. 1 atm condition. Okay, so here we, because of this, we use a mixture of sodium chloride and calcium chloride to help melt ice. Why? Because as we add ice, as we add this mixture to the ice, this mixture and water can form a solution at a temperature lower than 0 Celsius degree, right? Because when you add this mixture to ice, because ice is made of water, naturally it will start to dissolve this sodium chloride and calcium chloride. Therefore, the resulting mixture has a lower freezing point. Regularly, ice will what? Will be freeze at 0 Celsius degree. And now, if you add this sodium chloride and calcium chloride, they form a mixture. And the solution of sodium chloride and calcium chloride in water cannot be freezed at 0 Celsius degree. They will stay at, sorry. Amber nut. Yeah. Right? So you add sodium chloride and calcium chloride. And then sodium chloride and calcium chloride and water form a mixture. And this mixture has a lower freezing point. That means it will stay as a liquid below 0 Celsius degree. It could stay as a liquid at minus 10 Celsius degree. In other words, at 0 Celsius degree, regular water will be freezed. But if you add sodium chloride and calcium chloride to ice, the resulting mixture will stay as a liquid at 0 Celsius degree. It can be freezed maybe at minus 10 Celsius degree. See that? That's how it works. It helps to make the mixture, this freezing point depression can make the mixture stay as liquid at 0 Celsius degree, or maybe stay as liquid at even minus 10 degree. It depends on the concentration, right? If as we can see from this equation, if the molality, you add more sodium chloride, you add more this non-volatile compounds to ice, this freezing point depression will be what? Larger. It could be, the mixture could stay as liquid below 30 Celsius degree even. It depends on the concentration. If the concentration is high enough, it could, this water mixed with sodium chloride and calcium chloride could stay as liquid at minus 20 Celsius degree, or even minus 30 Celsius degree. That's how it works. And here's we can practice the end of chapter question 30. What are the mole fraction of this acid and water in the solution of this? What are the mole fraction? What are mole fraction? So, question 30, right? Question 30, mole fraction. So to answer this question, we need to figure out what? The mole of water and the mole of phosphoric acid. So first, mole of water equals what? 14.5 gram. And now we want to convert gram to mole, right? We want to convert gram to mole. And we know water is 18.02 gram per mole. They're equivalent. 1 mole of water, or either way. So we can just put one here. Here's the molar mass. 1 mole of water is equivalent to 18.02 gram. And then 18.02 gram is equivalent to 1 mole of water. They're the same thing, right? The same thing. And now when we want to convert gram to mole, we need to align. We need to choose the right conversion factor. And this one is the right conversion factor, right? or you can, you can put this water here, and water here. So you can do that, but sometimes that just makes things simpler, okay. Here. Then you can see the gram and gram cancel, right? The water here and water here cancel. Then we can get the mole of water. Right? We need to align the conversion factor in the right way. These two conversion factors are equivalent. They can be used at different situations. They're equivalent. We need to choose the right one. And then let me see. I think here I calculated wrong. I think I need to recalculate. 14.5
I think it's
grams.
supposed to be 125 grams of water.
You mean what? Excuse me?
I think it's 125 grams of water, and then
Oh,
the
yes, yes,
14.5 is.
Yeah, so thank you. Yeah, 125 grams. Thank you. So you got one bonus point for pointing out one mistake I make. So yeah, 125 grams, sorry. Yeah, 125. Okay, yeah, you're right. Well, yeah, 125. So thank you. Then so what's your name?
Mary Ellen Warden.
Okay, yeah, I just make sure. Yeah, I remember that. So yeah, thank you. So it's 6.939 mole. So anytime you point one mistake I make, you got one bonus point. So yeah. And then we calculate the mole of what? Phosphoric acid. 14.5 grams. Sorry. And then what's the molar mass? What's the molar mass? I think we can just easily find out. The molar mass, phosphoric acid. So the molar mass is 98 gram per mole. Okay, 98.0. So we need to put here gram per mole. At the same time, I will not, put this here. So we need to align the conversion factor this way. We cannot put the mole here and gram here, right? And this value needs to go together. Why? Because 18.02 gram water equals 1 mole water. So we need to align this way. We cannot put this value here. Cannot. This value needs to go with gram, right? Because that gram of water equals 1 mole of water. Then we can calculate the mole fraction. The mole fraction of, or we can just simply put X, water, equals what? Mole of water divided by total moles, right? Mole of water equals 6.93 mole divided by 6.9 plus 0.1.8. I think mole fraction does not have to be percent. 0.979. For the mole of this, you, again, or you can simply put, you can simply, just 1 minus mole of water, the mole fraction of water. Either way, you can calculate in 2 ways, right? Because the mole fraction, the sum of the mole fraction of every component should be 1, including the solute and solvent should be 1, right? Should be 1. Any question? Then no question, then we work on question 44. Assuming ideal solution behavior, what is the boiling point of a solution of that much iodine in that much benzene? Assuming the iodine is non-volatile. So question 44. So again, we need to work, right? We need the boiling point. We need to calculate the molality, right? The molality. So we need to calculate the molality of iodine. Molality of iodine equals what? Mole of iodine divided by kilogram of solvent, which is benzene, right? Right? We need to calculate. And now we don't know we only know the mass. The mass of iodine. Then we want to figure out the mole of mass. Yeah. We need to figure out 1 by 1. Okay. Iodine is 9.04 gram. Again, we want to convert this gram to what? To mole. And then 1 mole of iodine is equivalent to 253.8 grams. Oh, and you can check iodine molar mass. You Google iodine molar mass equals 253.8 grams per mole. That means 1 mole of iodine is equivalent to 253.8 grams. Or 253.8 grams iodine equals 1 mole. The same thing. But here we want to convert a gram to mole. Then we need to use this conversion factor. So we know the iodine, right? Now we know the iodine. We know the iodine, then we can put it here. And we need to figure out the kilogram of benzene. The kilogram of benzene, we know 0.75.5 gram. And we want to convert a gram to kilogram. What we should do? So we know here, I did not put 1 here. I did not put 1 here, okay, but there's 1 there, There's 1 there. Then 1 kilogram equals 1,000 grams, right? Sorry. So can we use this one? We cannot use this one, right? You see, if we use this one, we get gram times gram. You know, you got gram square, and you cannot convert. So here we need to do. You see that? Because we want to keep kilogram, so we put a kilogram up. We put this 1,000 gram down. So that gram and gram can cancel. Okay, so you see that? And then, this equals what? The molarity equals 0.472 molarity. And now we want to calculate what? Assume what's the boiling point. Then we go back to here. The boiling point. Here we change the boiling point elevation value. Delta T B boiling point. B means boiling. And then it times M times what? The molarity times Kb of benzene. Kb is what? Is the solvent boiling point elevation constant. And you can see here benzene. The Kb equals what? 2.3, right? Here the M equals, as we calculated, 0.472 molarity times Kb equals how much? 2.53. The unit is cells divided by molarity. Right? You see that the 1 divided by this equals this, right? 1 divided by m equals m to minus 1 power. Then this equals how much? 1.19 cells degree. You see, it increased the boiling point by 1.19 cells degree. And yes?
Are we going to have to memorize any of the constants for boiling or freezing
No.
points? They'll always be given?
No, you don't need to memorize.
Okay.
Yeah, so at this stage, yeah, well, you don't need to memorize this. Yeah, for the whole chemistry, you don't need to memorize this. Yeah, but you need to know the equation, you know. You need to know the equation and how to calculate. So the boiling point of benzene is what? 80.1 degree, right? The boiling point of benzene is 80.1. Therefore, the boiling point, temperature, the new boiling point equals what? 1.19 plus 80.1. So during the calculation, you always want to keep one more digit than necessary. But at the end, you keep the right number of significant figures. So here, you see, each of them has 3 significant digits, right? Therefore, for the final result, we will also keep 3 of them. We don't put 81.29. We don't put that. You see, because at the beginning, for each number, for each value, it has only 3 significant digits. Therefore, for the final result, you can only keep up to 3. But when we do the calculation, we can keep one more digit than necessary to be more accurate. So any question? There are quite a few us. Well, we discuss this later. Any question for this? Yeah. Then we move on. End of chapter, question 53. A 12.0 gram sample of nitrogenate is dissolved in that much water. The solution freezes at that much. Assuming ideal solution behavior, calculate the molar mass of the substance. So this question is related to lab 3. Lab 3, we are going to measure the molar mass of a solid by using this method. We'll measure the freezing point difference for a solvent, between a solvent and the solution, from the solvent. And then we determine the molar mass. How? Here's how. Okay. So question 53. Dissolve what? In water. Okay. The solution freezes at minus 1.9. So the delta TF equals how much? Delta TF will go back. Equals the freezing point of pure water, which is what? 0 Celsius degree, right? You see that? 0 Celsius degree. 0 Celsius degree minus the freezing point of solution, which is minus 1.94. So this is the freezing point depression value, right? And then equals what? This equals the molarity of the solute times what? The freezing, water's freezing point, depression constant, which is how much? 1.86, right? You see that? Times 1.86 divided by n. I'm sorry, but this m is a unit. Okay, this m is a real value. Okay. This m is a unit. This m is a unit, and this m is a value. It's really confusing. I think it's really confusing. Okay. Then here we know the molarity equals how much? .043 molarity. The concentration is that much. That's the concentration. And this concentration equals what? Equals mole of solute divided by kilogram of water, right? Kilogram is 80. Again, we want to convert this to what? We want to convert this to gram to kilogram. Right? We want to convert this gram to kilogram. And then this equals, and then from here, because this equals what? 1.043 molarity. And from here, we know the moles of solute, right? Mole of solute equals how much? Equals 0.08344 mole. Right? We count the mole. And how many grams? 12 grams. Then we know the molar mass, right? molar mass equals what? Equals mass divided by what? Mole. Right? And the mass is 12.0 gram. The mole is the molar mass is 144 gram per mole. That's how we calculate the molar mass. And our lab 3, we do this experiment. We measure the molar mass. Remember, we measure the molar mass of what? Of a liquid, right? Before, right? When we discuss chapter 9, we measure the molar mass of what? A liquid. Right? We make the liquid what? A gas. Right? And we use the ideal gas law to calculate the molar mass of a liquid. And here we use this method to what? We use this method to figure out the molar mass of a solid. So, well, yeah, I think we'll stop here for this, and then you can start to work on in-class assignment and question. Yeah, I posted to Moodle, and you can check. Question 36, 42, 46, 60. You may not be able to answer all of them. You can just, remember you can work on question 36 at least. Any questions? Oh, yeah, and then we'll discuss how to do calculation for lab 1, because quite a few of you contact me. There are really, yeah, I know it's not easy because it involves some physics. You see that you need to know how to calculate the pressure. So we'll discuss lab 1. So get prepared. If you don't know how to do the calculation, we can discuss. Okay, we can discuss because it's due tomorrow. It's due tomorrow.